Okay, that was not rhetorical. But anyway, we could just get started. Welcome to the last slot of this year's Wednesday EclipseCon day. So I'm between you and the party, and I welcome all of you to this cozy atmosphere here. So if you fall asleep because of oxygen consumption or lack of oxygen, please avoid snoring too much. My name is Sebastian. I'm a consultant and language engineer at Itemis, and I want to talk about pluggable type systems for Java. Who of you embraces static typing and type checking and wants early feedback from the compiler? Who of you has never seen illegal argument, illegal state exceptions, or null pointer exceptions? One. You are hired. So even though Java is a statically typed language, we still see things like class cast exceptions, null pointer exceptions. So to me, a clear sign that the type system in Java itself is not powerful enough. It is already very helpful, so I don't want to compare writing Java code to writing code in a language like JavaScript, where basically everything is a valid program from the compiler's perspective. But we still see occasional errors that could be detected by a smarter compiler. And this talk is about mechanisms, how we can make the Java compiler itself better at detecting statically known problems in our code. The tool that I want to present is the Checker framework. Today I'm only presenting university projects that are not ready for production environments. But anyway, the Checker framework is an enhancement to the Java type system that claims to have a sound implementation for various statically detectable problems, so that your code can provably never throw things like null pointer exceptions in your face. This is a bold claim. We have heard that some probably before, like with the JDT null annotations that already helped there. But Checker framework makes this claim anyway. How does it do this? Well, by raising static errors during the compilation process and by hooking into the Java compiler. The mechanism to do that is the APT interface of the Java compiler. It's a standard defined for all valid Java compilers, so being it Eclipse compiler for Java or Java-C, all offer this API. And we can configure this in our projects and just enable the annotation processing, and then we could register annotation processors. So what is an annotation processor? An annotation processor is a small tool that runs in the context of the compiler, that you provide this tool, you provide an implementation that will be executed whenever an annotation occurs in your source code. So the vehicle is annotation in source code, APT registered for the compiler, and then you can run your code and issue errors and warnings. The Checker framework itself comes with an impressive list of available default checkers, and also with an API to define your own compiler plugins. And this is just a small excerpt of the available checkers. So the most prominent one is the Nullness Checker that will help you to avoid and mitigate any null pointer exceptions in your code. We'll see in a short demo what this means. Then we have a checker for interning of objects. So back in the days of Java 1, we had this idea of object pooling for all objects. Then we learned, well, the JVM is pretty good at creating new objects and discarding instances again. So we only pool expansive instances and strings because we can sometimes. And the interning checker helps us for situations where our own code base has pooled objects. When you have ever written regular expressions with a reasonable complex syntax, you've probably seen pattern pass exceptions at runtime. There's a a compiler plugin that tries to detect those already at compile time. Same for format strings. So you hand over too many arguments to your format string or too few arguments of the wrong type. Usually you only see the feedback at runtime, and there's an implementation that will do this also at compile time. Then we have one of my favorites, the signature string checker, that helps us to write reflective code. Of course, no one would ever write reflective code, but just in case, you see there's tools that help us, and a checker for units, so time units, distance units, things like that, and for unsigned versus signed comparison of numbers. So when you remember that back in the 60s or 70s, I should have looked up the exact year, there was a very big bug in a piece of software that was supposed to shoot a rocket into space. So they compared imperial metrics with the metric system, imperial distances or times. Anyway, the thing exploded, and that was because of a bug that could have been detected if we had stronger checking for subtypes and units. So let's go into a few examples in more detail here. I want to start with the units example. So the checker framework allows us to write code like this. I still use primitive types, so I can still use operators in Java, plus, minus, multiply, etc. And I annotate the types as being unit types. So I can say this is unit meters and this is unit seconds, and then I can divide meters by seconds and I get meters per second. This is kind of an example that I want to show now also in Eclipse, along with the second part, which is a declaration of such an annotation. So let's see. Here's my small demo project. I have the checker annotations on my class path. I have, for the sake of the argumentation, no mic anymore. Also the JDT null annotations on the class path. And I want to start with a demo on units. Is that visible from behind? Yes. By the way, if there are any questions or so, just raise your hand or shout at me, and then I will try to answer those. So we have meters, we have seconds, and we have meters divided by seconds and get meters per second. What happens if I change the operator to a multiply sign? So far, nothing. And this is where the downside of the checker framework starts. Even though there is an official API to write compiler plugins, this API only exposes the structure of your types and not the ASTs. In order to inspect the expressions, we need the AST. So we need to know that there's an assignment, which is a binary operation with a left and right operand, etc., etc. And this integration was kind of hacked into Java C. So the Eclipse integration for the checker framework is a little bit questionable. So at least we have a menu item here. And then I can say, please run one of the checkers, and I want to run the units checker now. And now I get, it issues a warning that says, well, what we have here is an expectation of meters per second, but what you actually did is meters times seconds, and I don't know what this is, so it's most likely a statically knowable type error. So far, so good. So what happens if I want to use the unit kilometer now? And I want to say meters times 1000, and I cannot use the quick fix because it's lowercase, but still, organized imports will import the annotation. And if I run now the checks, again, it will issue new warnings and says, well, you multiplied meters times 1000, so now you have 8000 meters, but not yet kilometers. So for that, for unit conversion, you sometimes have to use also the unit tools. which has a nice method to do this. And then I get the proper results. Let me fix this here. So now this, the compiler is happy again. One important concept of the checker framework, despite that it offers all these nice units, is polymorphic treatment of units. So sometimes you have generic operations that should be able to cope with any kind of unit. So I want to be able to multiply meters by a certain amount. So I want to make 10 meters times 3 should be 30 meters, or 10 seconds times 3 should be 30 seconds. And for that we have a way to express it as well. So let's say I have more meters, and it's supposed to be meters times 3. When I now run this check, it will again issue a warning that it doesn't know what it's supposed to do with this. And in order to express the polymorphism with the units, we can use the annotation called polyunit. So I say this function can cope with any kind of unit, and it returns the very same unit independently from what I gave it there. So internally it will replace all occurrences of polyunit by meters in this method invocation, and so I can get rid of the compiler warning again. Makes sense so far? Maybe. Next example. So that was kind of the baseline. What we see here now is the annotation for kilometers, and how it's related to meters can be deduced just from this declaration. In fact, if you're familiar with all the stuff around this, so we can ignore this. This is Java standard stuff. Then we have the information that a kilometer is a length. So this is our actual type. And we are related to the meter annotation, and we basically prefix this with kilos. So there's the relation of having this multiplier or this division by 1000. So it's not a fixed set of annotations that's supported, but we can implement our own annotations as well. More prominent examples. The nullness checker. Enough has been said about the $billion mistake. So yes, dereferencing null is a bad idea. Doesn't work usually. And Java with or Eclipse Java with the JDT compiler already helped to mitigate the issue by providing the null annotations. So for the sake of the argumentation, I enabled all the fancy options that we have on our project. So everything that's possibly a null pointer access will be an error or a warning. So I made the compiler shout in my face whenever it thinks something's going wrong. And the consequence of this is my second example. This is what we have here. We have a main method, and I want to print the class loader of a given class. And I want to say my class was loaded from this class loader. Is this code sane or not? Can anyone spot problems here? So we all agree that this is fine. Even the JDT compiler says everything's good. I can run this method, and it will print something like this was loaded from the app class loader. Second example. Now let's make it different. Let's say I take args get class, and I want to see the class loader that loaded the string array type. Still everything good. I can run this, and bam, null pointer exception at runtime. So despite the fact that I enabled all this stuff in this class that JDT can provide to me, it's still throwing null pointer exceptions. What happens? Well, we don't know yet. So let's run the checker framework on the same class. It will do its thing, and then it says, well, here, this guy could return null. So obviously, that is a problem in our code that was statically detectable. Still, we shipped to production and ended up with an MPE. So how does it know that this could be a null reference? I don't know yet. Let's check why it was returning null. And then there's blah, 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 javadoc, javadoc. And the first sentence is, some implementations may return null for a subset of the classes, every class that was loaded from the Bootstrap class loader. Okay, that is impressive. It told me this up front. How was that possible? Well, what they did is they stopped more or less all the JDT classes, all the JRE classes, and it almost makes it into the line, and says, well, the method getClassLoader is actually nullable. So they annotated all methods from all Java standard types, and the annotation processing itself is run against this annotated library. So this gives us more information than the JDT null checks could ever have, and thus it issues more warnings to me. And I can safely assume that if C was from a Bootstrap class loader, then getClassLoader would return null, so I would need to write different code in order to get the class name. Different example, but more or less the same story. I want to print the component type of an array type, so I say my class is never returning, is never null. I can run this, and it will give me the name, and when I use a different type, it will again throw a null pointer exception without the compiler telling me. What happens here is a similar story. So I say run this selected checker, nullness checker, and it says, well, component type may return null, of course, if it's not an array type. So in this line, we have a dereference of a possibly null value. What we can do now is add a guard. So only if my class is an array, I want to do this. And if I run the checker now, it's green again. This is because, again, the same story. They annotated all the libraries for us. So the method isArray. It's annotated like this. It's a native method, okay, it's pure, so it doesn't cause any side effects. That's for a different checker. And it ensures that another method will not return null if this returned true. So it ensures that getComponentType will not return null when isArray was invoked. And this information is actually used by the checker to prove that we don't see any null values in our variables here. And the last thing that I have for the null annotations is this fancy logic. Apparently, examples tend to use names for sophisticated computational intensive operations. So we want to cache the length of the name. So whenever someone sets the name, I say the full name is the full name, and I want to update all the cache values in our private method. And here I say this .fullname.length should be stored. So far, so good. I bet this code is okay. So I will run the checker. And now I see that something's not initialized. So this is, now it gets funny. Even more so. So what happens? I create a new instance of example 3 and the full name is still null. So full name is effectively nullable, but the only setter that I have will never set a null full name. So I can be sure that update cache sees never a null value. What I can do now is apparently not a simple thing like annotate in the full name as non-null because it's not initialized. So it is effectively nullable, but what I can say, it's monotonic non-null. That's an annotation from the checker framework that says this value may be null, but as soon as you start assigning a value to it, this value must be non-null. And afterwards, I say run the checker. Afterwards, I see a warning again that full name may still be null here. That's because we don't know yet that update cache is only called from this method here, because there may be different methods that also invoke update cache without notifying me. And what I can do now is I say this is requires non-null full name. And now it's sound again. And the purpose of this requires non-null method annotation is, of course, that I have the option to say do stuff and update cache. And in this method, I don't have a proof that the name was already set. So this is a statically known programming error. And now it highlights that update cache may not be called without ensuring that the precondition is met. So we have a different set of annotations than with the plain vanilla JDT annotations. We can express information about the control flow that we expect in our application. And we can also model the relationship between different states of our types by ensuring that certain methods are invoked before others are invoked. Let's go back to the slides here. Null annotations. As you have seen, I had the JDT non-null and null annotations on the class path. Apparently, there are more than just the JDT and the checker annotations. So we have Lombok, we have Android, we have again Java org Eclipse with JGit. We have some JavaX annotation from some JSR that is dormant. We have another JSR with annotations that are, say, not null, and so on and so forth. So different annotations to indicate that my code will not return null or accept null as an argument. All these annotations are treated equally by the Nullness Checker of the checker framework, whereas the longest qualified name, not even the biggest, but one of the longest also, biggest in font size, is the one that is shipped by the checker framework itself. So this is quite nice because your libraries that you have on your class path will all use different types of annotations to indicate the same information. And to take all into account, you just use the checker framework. And then the analysis will be more sound than without it. A few words on the impact of annotating your code with nullable. So what is implied by these annotations, and that's why I'm calling this talk Pluggable type systems, what is implied is that the type system is changed for Java. So a default reference in Java is implicitly a nullable reference, and only subtype and the non-null equivalent would be a subtype of the nullable reference. So assignability is I can always assign a non-null instance to a nullable instance, but not vice versa. On the other hand, we have the standard inheritance relationship between Java classes, like date is a subtype of object. So of course, nullable date is a subtype of nullable object. And then we have diamond inheritance here, which cannot even be expressed on the class level in the Java type system, to say that a non-null date is both a non-null object and also a nullable date. But this is all nicely documented in the quite good manual of the checker framework. So what else do we have? The object pool idea is taken to an extreme by Java itself. So we are sure that these two string constants are actually constant in the entire JVM. So it's safe to compare them by identity comparison. Let's say I run the interning checker here. And now it highlights this line and says, well, you could skip the method call and can replace it by equality by identity comparison, and when I say don't use the constant but create a new string, then of course we see a different error or different warning, because now these two lines are not sound anymore, because they probably indicate a programming error. And I can mitigate again by using string intern here, which will make sure that we again see intern instances. Why is this useful? Well, in practice, I would say not at all. But there are popular frameworks like EMF, for example, that do object pooling with URIs. And in that case, we can safely compare all URIs in EMF with the identity comparison. And this will avoid null pointer exceptions as follow-ups, because the equal method will always produce a null pointer exception if the left-hand side is a null value. So for some cases or some not so common coding patterns, it may be helpful to run such a checker on your code base. This one is one of my, well, this is a little scary actually, concurrency semantics. When you have attended Olaf's session yesterday on locking and parallelism in Java since 1.0, you know that there is synchronize and there is re-entrant, read-write lock and all these things. And all these are prone to deadlocks or live locks when it comes to a situation where you have more than one lock in your code. So as soon as resources are acquired and in this synchronization block another resource is acquired, it may happen by accident that you acquire them in different order, or that you use fields that are supposed to be guarded by synchronization in unsynchronized code. And the lock checker helps us to detect those situations by imposing a very strict type system based semantics on the entire synchronization topic. So one more example here, and it still makes it on the slide, yay. So we have a re-entrant lock here, Java 5. We say access to X is always guarded by this lock. And then we have a method that works with X. We have a method that should not be blocking at all. And we have an example method that accesses X and also calls my method. So when I run a checker on this one to detect concurrency problems, then it will highlight a few problems here, because all these methods use the variable X, and X is supposed to be guarded by a lock. Now I would need to rewrite my code to fix this. So first of all, I say should not lock, should never lock. So I'm doing fast forward, and then make it look like this, because typing is not my superpower yet. Still, we are guarding the access to X by a lock. We say my method is only invoked when I have a lock. We say should not lock, should never lock. And we say this one, the example method, it may release locks. So we are not sure whether after the method was exited, we still have a lock. And we guard the access to X and also the invocation of my method by this lock object here. And if I run the sanity check, then we see only one problem left. So it figured in the control flow that these preconditions are all fulfilled because I obtained the lock, because I released it, this annotation is necessary, and this code is invalid because I tried to work with X, but actually in a method that should never obtain any locks. So I cannot access X here, and would rather use something like this, and make sure that x was given as an argument into this method should not lock. Regular expressions and format strings, super useful but not extremely impressive in the end. So it will just check the validity of these format strings, whether the number of arguments matches the number of placeholders, so these two examples, whether the types match. That's pretty much what I already said in the introduction. And here this is a completely illegal syntax for a string format, and that would issue a warning as well. And of course we can do the same for regular expressions. When we have patterns with placeholders and things, we can detect broken patterns there, also statically at compile time. Who has ever read about SQL injection? Or yeah, everyone. And no one is we are never safe of untrusted data sources, but within our code we are often pretty sure that some values have already been checked and others were not checked. So of course we can use annotations to mark information that came from our internal methods or information that came from untrusted data sources by using tainted or untainted annotations. And last but not least, who has ever used the wrong method of these when it comes to reflection? Why is that? Because strings are horrible and oversimplifying. So when we say this is a class and I want to load it reflectively, which one am I supposed to use? Is it getName, or is it toString, or getCanonicalName? Well, in the end, a few of those may work. So this one is definitely broken. GetName and getCanonicalName would usually yield the same result, except for a few corner cases. In any way, what we want to be sure of is that the types are really the right ones. So we can run a checker here as well, and we'll say it will yield a warning that class for name accepts only fully qualified names, but we only class getName values, but we passed a fully qualified name here. And under the covers, it uses this class diagram to deal with the different types of strings that you could by accident or on purpose obtain from Java-Lang class objects or from the Java-Lang Reflect APIs. So there's certainly different representations of the arguably same information when it comes to Java-Lang classes. And of course, this is then consequently error prone when you pass these strings around without proper information where they came from. So thus, the checker framework ships with a signature checker that allows us to ensure that we never use canonical name when we want to use the Reflect API, or that we only use the canonical name, let's say in error messages that will be shown to the developer or even to end users. I don't know, probably to the developer. All this stuff is available as GPL2, so same as the OpenJDK Java-C compiler, and the annotations themselves that will become part of your code base and not only the vehicle to compile your code base are available under the more permissive MIT license. As you saw, integration into Eclipse is kind of so-so, not so nice, but integration into Maven and Gradle, Java-C command line compilation or something else is all pretty seamless. So when you want to give it a try or give it a shot, I recommend using it from like build systems and not from Eclipse, because I wasn't able to run this on Oxygen, for example. So this was still Eclipse Neon. So this was my take on more powerful type systems and the available technology that is already out there and ready to be tried, ready to be used, maybe not, but ready to be tried. And of course, this is open source and they are accepting pull requests and all the things. And if there aren't any questions, I would say thank you. Yes.